This lesson covers the subject of runway contamination and its implications for aircraft takeoff and landing performance. To help you understand what is meant by contamination, we shall start with a few definitions. The term contamination is often used by aircrew in a fairly general sense to refer to any precipitation on a runway surface. But the word actually has a specific meaning in this context. A runway is said to be contaminated when more than 25% of the surface is covered by any of the following: surface water more than 3 mm deep, or slush or loose snow equivalent to 3 mm of water. Snow compressed into a solid mass which holds together or breaks into lumps if picked up, referred to as compacted snow. Or ice, including wet ice. A wet runway is one that is covered with water, or equivalent, to a depth less than that defined as contaminated, or has enough moisture on the surface to give it a reflective appearance, but without significant standing water. There are a few other terms used in connection with precipitation on runways. A damp runway is one that is not dry, but does not have a shiny appearance. A runway can be termed dry when it is not damp, wet or contaminated, the category including any paved areas which are either grooved or have a porous surface designed to give dry braking action when moisture is present. Some operations will inevitably have to take place on wet or contaminated runways, with due adjustments to landing and takeoff distances. The factors are covered fully in the performance syllabus. However, takeoffs should not be attempted with a dry snow depth of more than 60 mm, or more than 80 mm of very dry snow, or in more than 15 mm of water, slush or wet snow. A potentially serious hazard that can be encountered when operating from water-contaminated runways, that is, with more than 3 mm, is aquaplaning, also known as hydroplaning. During a takeoff or landing run, it is possible for a tyre to ride up over a layer of water, which has not been displaced by the tyre, which results in the wheel losing contact with the runway. There are three types of hydroplaning, known as dynamic, viscous and reverted rubber. Dynamic hydroplaning is generally associated with a rotating wheel, spin down, on takeoff from a flooded runway when the critical depth of water is greater than the tyre tread depth. As the tyre speed approaches a critical speed, known as hydroplaning speed, a wedge of water builds up in front of the tyre and lifts it clear of the runway surface, thus affecting braking and directional control. The ground speed in knots at which dynamic hydroplaning occurs can be calculated by using the formula for a rotating tyre, spin down, which is multiply the square root of the main wheel tyre pressure in pounds per square inch by 9. Viscous hydroplaning occurs when a wheel locks up on a smooth surface covered by a thin film of moisture, where typically on landing, a wheel may skid or lock up, spin up, thus affecting braking and directional control. The ground speed in knots at which viscous hydroplaning speed occurs for a non-rotating tyre can be calculated by the formula 7.7 times the square root of P, where P is the pressure of main wheels in pounds per square inch. It is worth knowing that incorrect tyre inflation pressures or badly worn tyres will have a serious effect on the hydroplaning speeds. Therefore, it is good airmanship to ensure that aeroplane tyres are in good condition, have adequate tread and inflated to the correct pressure. If the tyre pressures are quoted in bar, the value should be multiplied by 14.7 to obtain the equivalent in psi before doing the calculation. In the event that a tyre is hydroplaning and the available friction is insufficient to rotate the wheel, a lot of heat will be generated converting the ice or water into steam. The converted cushion of steam lifts the tyre off the runway, eliminating tyre-to-surface contact, and the steam heat reverts the rubber to a black gummy deposit on the runway, causing the wheel to skid, thus eliminating braking effectiveness and directional control. To give pilots some idea of braking performance under various conditions, a table of braking action was produced based on operations on snow, ice and rainy runways, relating a measured braking coefficient to an estimated braking action. From that, a simple code was derived, but the values in the code and the verbal descriptions are relative to the runway conditions, which means, for example, that code 5, good, on a wet runway would be safe, controllable conditions, but not as positive as on a dry runway. The friction coefficient under any set of conditions would be measured by a mu meter or equivalent towed along the runway, usually by an air traffic control vehicle. The device is towed at a given speed, typically 40 miles per hour. It has 3 wheels, the rear central one measuring speed and distance, and the front 2 which are angled slightly inwards or towed in, sensing the friction between the tyre and the runway surface. The coefficient is a measure of the difference between the braking effect on a dry runway and that on a contaminated runway for an aircraft at a given mass and speed. The coefficient will vary with speed, being around 0 at very low speed, rising to about 0.5 at 100 knots, and decreasing slightly with further speed increase. Thus, as an aircraft slows down below 100 knots, its braking performance will improve. For all takeoffs and landings, runway length is an important consideration. For takeoff, it is not just a question of whether there is enough runway to get airborne, but also whether there is enough to stop in the event of a rejected takeoff. For landing, there must be sufficient runway in which to brake safely. In both cases, deposits of water, snow, slush or ice on the runway will increase the distances required, either for the poorer acceleration due to the drag caused by the deposit, or for the loss of friction during deceleration. In all cases of contaminated or wet runways, there will be a percentage factor to be added to the calculated performance distances. EU OPS regulations demand that operators ensure that the distance available for landing is at least 115% of the distance required, but this may be reduced if the relevant flight manual contains specific information on these conditions. This lesson need not detail all the factors applied for the various conditions, as these are all covered in the performance syllabus. However, one further factor worth considering is the effect of heavy rain or spray on turbine engines. Large amounts of water ingested by the intakes can cause power fluctuation or even flame out, so it is recommended that continuous ignition is selected to avoid power loss at these critical stages of flight. Some limitations may apply in the case of contaminated runways, and the procedures associated with takeoff and landing are to be found in the Operations Manual, Part B. For example, to reduce the possibility of a crosswind component aggravating any tendency to swing the aeroplane on landing, it is usual for an aeroplane manufacturer to reduce considerably the normal operating maximum crosswind if landing on a contaminated surface. When operations are required on snow or slush contaminated runways, a Snowtam is available to the flight crew. The Snowtam contains information concerning the friction measurements on each third of the runway. A sample Snowtam for Munich is on screen. The validity of the Snowtam is 24 hours. The two significant items in the decode list are G and H, where G indicates the mean depth of the slush, 1 mm over the entire length, and H the friction measurement for each third of the runway. The three friction measurements of 0.35, 0.26 and 0.26 represent the braking action for each third of the runway. If snow is on the runway and there is a section which has not been cleared, reference to code items D and T will explain the situation. In the code section, item D will represent the cleared runway length in meters, and item T will describe the uncleared length in meters. The sum of the two measurements should equal the published length of the runway. In this lesson, we have looked at how rain, snow, slush, and ice on runways can have significant effects on aircraft takeoff and landing performance. Pilots need to be aware not only of the allowances that need to be made in their calculations before flight, but also of the hazards that they may encounter, such as hydroplaning and water ingestion, which require prompt and correct action. Advances in tyre and runway surfacing technology have helped decrease the risks, but the pilot's skill and airmanship will often be the deciding factors in marginal weather conditions.